everybody. My name is Michael Labib. I'm a Specialist Solutions Architect here at AWS. And I'm super excited to be speaking with you about Amazon ElastiCache for Redis. So we recently released a lot of really awesome features that we're going to go through in today's talk. And just a level set, we're going to start off, kind of getting everybody on the same page with what Amazon ElastiCache is. Then we're going to dive into how do you scale your Amazon ElastiCache cluster with online resharding. Then we'll review, our security footprint with respect to, how do you set up that topology and the networking and all those infrastructure associated with your cluster, as well as encryption, which is a new feature that we just recently announced. And then we'll take a look at some common usage patterns that a lot of our customers are using today. And then we'll close off with best practices. So year after year, we're hearing increasingly from our customers this need for speed. And this is really coming from virtually every workload and every vertical that you can imagine. So what customers are essentially asking for is they in their data platform, they want a fast data layer, right? And this need has developed to the point where we're no longer measuring performance in milliseconds. This is a microsecond, sub-millisecond gauge. So this is really where Amazon ElastiCache fits in. Amazon ElastiCache is an in-memory key-value store. We support the two most popular key-value store engines, Redis and Netcache. It's fully managed, zero administration, no racking, stacking, failover that you have to worry about. And it's hardened by Amazon. And what does that mean? What it means is we have some engineers who are involved with the open source Redis product, and they are constantly looking at the engine and the features, and then we evaluate what our customers are asking us for, and we enhance those areas that we feel better serve our customers. So if you were to take a second to think about your data from a temperature gauge, the hot data would be that data that you access most frequently. And if you thought about the characteristics of that hot data, what you would want it to be is the ability to support incredibly high request rates, very low latency. And that's basically where Amazon ElastiCache fits. And as data volume grows and sort of the data starts getting warmer and colder, you'll see SSDs and you'll see other data stores sort of fit in. Now this is not a bit or an OR operation. So if you're building a data platform, essentially what you want to do is you want to think about your data access patterns and you want to utilize the different data stores and databases that make sense for that specific data access. So Redis, quick overview, just a level set, make sure everybody here is on the same page. Redis today is the most popular key value store in the market. And the reason it is because it has a variety of different features. It's a Swiss Army knife of key value stores. It has a variety of different data structures. So if you're a developer, a lot of these are, they ring a bell to you. Hash maps, lists, sorted sets. And it's very intuitive with respect to how do you use Redis. In fact, I like to think of the API as, sort of genius because it's very rich in capability, but syntactically, it's very predictable and very easy to use. Other things that make Redis very interesting is that it supports HA. So you can have a master or a primary or multiple primaries in a clustered environment, and then you can fail over in the event of a failed scenario. And what does that support? It gives you that added HA that you need for those critical workloads and those solutions and infrastructures that you care most about. Other things that's great about Redis, it's open source, and Amazon ElastiCache fully supports the open source version. So from a syntactical standpoint, from a protocol standpoint, it's a drop-in replacement. And another cool feature is it has transaction support. So you can have a multi-execute various different commands in a transaction block, which simulates that transactions. And just like the commercials, there's always more, right? So other things that Redis has, it has Lua scripts. So you can bake in business logic that you can call and reference within your Redis cluster. There's geospatial capabilities. So geospatial supports a special sorted set that supports longitude and latitude. This is great for mobile applications where maybe you're passing location-based information to the cloud and to Redis, and you're looking for points of interest that you want to serve to your end users. There's pub/sub capabilities. So this allows you to build chat applications and notification systems. And it's just built into Redis. So there's nothing that you need to turn on. There's no additional cost. It's just there. Now, in terms of ElastiCache features, ElastiCache offers a variety of different ways that you can deploy and monitor your Redis cluster. And a lot of these are familiar to you because we support these in other services as well. So AWS CloudFormation, template engine where you can run JSON, YAML scripts. And this is great for infrastructure as code. So you can build what you would want your application and Redis cluster to look like, how many shards, what node types, all those sort of details with respect to your cluster. You can versionize that template and then build it whenever you need to. I use this all the time when I want to do benchmarking or performance testing, and once I'm done, I sort of turn down or collapse that stack. Other capabilities is CLI, SDK, so all the operations associated to ElastiCache you have full control on using the CLI and SDK. The SDK you'll use in your applications, maybe in Lambda functions. And then CLI you'll have through the AWS CLI tool. And then if you don't like a lot of excitement in your life, there's always the console, right? So a couple clicks and you can build a Redis cluster that way as well. From a monitoring perspective, there's CloudTrail, AWS CloudTrail, and so this gives you all the log essentially of every interaction to the service, when it happened, who did it, that sort of thing. AWS config, which is great to build compliance, how you want that cluster to look like. Amazon CloudWatch, which I think pairs very nicely with Redis. And so what's cool about CloudWatch is in addition to us funneling up all the Redis info data through CloudWatch, you also can be very proactive with respect to this. And how do you be proactive is issue an alarm, set a metric that makes sense to you, issue an alarm, consume that alarm through an SNS notification, and then do something interesting, right? Maybe have an operation on your cluster. I'm going to have an interesting example about this later in this presentation where we'll revisit that architecture. Other things that we've done, so I mentioned earlier that it's fully open source compatible. Our engineers are very involved with the open source project. But we also have some enhancements that we've built into ElastiCache. I'll review some of these. So the first one is a background save operation, so optimized swap memory. So with Redis, especially if you have a lot of writes happening to your primary, if you were to do say a snapshot, what happens is you have the possibility of doubling your memory footprint. Right? This is true for open source Redis. And so what that means is if you wanted to be safe and conservative, you would want to reserve 50% memory just for those background operations. So we took a look at that and we thought we could do better, right? So what we wanted to do is we wanted to give our customers the ability to use more memory without putting them in a situation where it would sort of create a possible problem, right? So what we did is we changed the algorithm with respect to how much memory you have available in your cluster, and if we detect you have less memory to do that fork-based operation, we'll do a forkless operation, which is essentially a timer task job that will do this background snapshot in a more efficient way. The second feature that we did with open source Redis, if you're experiencing a lot of writes to your primary, and your primary, say, is under a lot of pressure, maybe memory is very low, there's the possibility that your replicas might fall out of sync. And that's not a good scenario. So what we did here is to protect your primary against failures, and also to reduce the possibility that your replicas are out of sync, we'll throttle some of those writes. The they'll still execute successfully. We'll just slow them down just to make sure everything here is consistent. And again, this is only in a scenario where you're doomed for failure. So we're sort of mitigating that possibility. And then the other one, which we actually contributed to open source, it's in Redis 4 today, is referred to as psync2 in the open source Redis. And essentially what it is assume you have a primary and multiple replicas. If that primary fails, an election takes place where one of your replicas becomes the new primary. With open source Redis prior to Redis 4, all the other replicas, essentially all the data gets flushed, and then they have to resync the entire, or rehydrate all the data from the newly elected primary. So what we wanted to do is make that whole failover process more effective, more efficient. And we rewrote that in an earlier version of ElastiCache, and we contributed a lot to that, to the open source. So some of our engineers, there's as I mentioned earlier, there's been bugs, there's been various things that we've done ever since 2.8, and I wouldn't imagine this trend to change. So we support the open source project. This is a trend that we're going to continue, obviously, to support. Now, Redis comes in two different flavors. There's two different topologies. The first one is a vertically scaled environment, and what that means is you have one primary. All your entire key space, which is the 16,384 hash slots, they live in that one key space. And so what this means is all your data can fit to the largest size of that node, and in this case would be an R4 16XL, which is 407 gigabytes. And your replicas have the entire copy of all the data, right? What we would provide you is a primary endpoint. Your applications would point to that primary endpoint. You'd also have the replica endpoints. And if there was a failover, what would happen is we would take that primary endpoint and we'd propagate that on one of the replicas. So we do the DNS swap for you. Nothing has changed with that topology. We still support it. But cluster mode enabled, there's a lot of new things, so we're going to focus in this talk on cluster mode enabled. So with cluster mode enabled, what we're doing here is it's basically a horizontally scaled environment. So you have up to 15 shards. A shard is made up of a primary and 0 to 5 replicas. And each one of these shards essentially owns a portion of that key space, right? So it's a hash slot range. And a default distribution would be to divide the hash slots across the number of shards that you have. So that essentially is the difference. The other thing with a cluster mode enable is we give you a configuration endpoint. And in your Redis cluster aware client, the way it works is it would communicate through that configuration endpoint. It would get a map of all the topology in the nodes associated to your cluster, and it'll know exactly which node and which shard to target for a specific key on a get set-like operation. Now, there's other differences. So we'll sort of kind of recap a few other things between cluster mode enabled and disabled. From a failover standpoint, because there's no DNS involved, cluster mode enabled is much faster. So if you care about failover speed, enabled makes a lot of sense, right? Because a failover may take somewhere in the neighborhood of 15, with the worst case scenario, 30 seconds. And remember, this is on an individual shard. So imagine you have 3 shards, and you had a failure on one of them. Only 33.3% of your data is affected. And if you wanted to reduce that blast radius even further, all you would just do is add additional shards. So the failure risk is also a better option for you if you wanted to lower the impact of failures using Redis. You would go with the enabled version. The other difference here is with respect to performance. Because you have the ability to have many shards, you have the ability to write to many primaries at the same time. Because again, a shard consists of a primary and its associated replicas. So from a writing and from a reading perspective, you have more nodes to interact with. So its performance is going to be greater. The obvious difference here would also be storage. So because you have more nodes and your data is spread across many primaries, you can have 6+ terabytes worth of data in a cluster mode enabled topology. So that's massive, right? More connections. The one trade-off here is cost. So the cost may be more expensive because you have more nodes. However, when you are architecting using cluster mode enabled, you're selecting smaller size nodes versus a larger node. But the cost is certainly more expensive with enabled. So that would be your trade-off. Let's take a deeper look at cluster mode enabled just to make sure we're sort of all on the same page with how it works, under the hood, that sort of thing. So I mentioned earlier, Redis has 16,384 hash slots. And again, these hash slots are divided by the number of shards that you have, and that would be the equal distribution, although you have control on changing that. And a key essentially finds itself in a slot after doing a circ16 modulo function. And after it does that, it'll live in essentially a slot, and then the client that you're using, whether it's a Java client, .NET, Python, as long as it's cluster aware, it will ping the cluster, issue a cluster slots command, and it'll get a map of the topology, the nodes, and also which node is associated to what hash slot range. So it knows where to direct the traffic. It also knows which node is a primary, which nodes are replicas, things of that nature. Now, all clients are different, so you obviously want to look at the different characteristics of each client. But that's generally how the smart clients work. Now let's sort of visualize this. Imagine this is your cluster. This is an example of a 3-shard cluster. Each shard here will be a different color. And the border, that gray border, is we'll kind of note as the primary. Now again, a cluster can be made up of 15 shards. And a shard can have up to 5 replicas. So if you look closely here, the replicas have the same hash slot range of the primary. And this is true, obviously, for all 3 shards. And what happens in a failure scenario? So imagine one of your primaries failed. The impact that you have is only to the writes. You can always read during a failure, assuming you have a replica. Now, for 15 to 30 seconds, what's going to happen here is we're going to detect the failure, and then we're going to immediately elect one of your replicas to be the new primary. As soon as that election happens, your client is made aware of that election, and it'll be able to start writing to that newly elected primary. Now, if you wanted to reduce, again, as we mentioned earlier, that blast radius, you just add more shards. Right? So if you had 10 shards, only 10% of your data would have been affected in a failure scenario like that. Now, what happens if you lost majority? This is another difference that we have with open source. So with open source, if you lost the majority of primaries, you have a problem now with the election. And your cluster is unable to elect a replica, a suitable replica, to be the new primary. This is something that we added some enhancements around, and we're able to make an intelligent election here, and your cluster is recovered. Again, this is nothing that you need to do. There's no intervention. This is something that we're managing for you. So the question here is, all right, well, imagine you have a cluster of 3 shards, and you wanted to go to 5. How do you do this? There's an old way, and I'll just call it the old way for now. And then there's a way that I'm going to introduce shortly. So the old way would be, and this is only for cluster mode enabled, is to leverage backup and restore. And we'll talk through why this is not efficient as we're kind of building up this slide. So the way you would do it is you take a snapshot of this 3-shard cluster, and after you take that snapshot, there's an obvious thing that you're noting here is that any new writes that are happening to your cluster are not captured in that RPO or that snapshot, right? So you're going to have to mitigate that, but we'll come back to that. So after you take the snapshot, what you do is you copy that snapshot, you place it into your S3 bucket, then you create a new cluster, and then you pass the RDB files that were associated to the 3-shard cluster that you had to the new cluster that you're creating. So you're hydrating this new cluster with whatever shard count that you wanted. We'll assume 5 here. And then what we'll do is each shard, remember, it has, it's designated a certain hash range. It will discard whatever, keys or slots don't belong to it. And so the slots would distribute across the five shards. And then after you've created that cluster, then what you're going to do is you're going to point your application to this newly elected cluster. There's a new endpoint. There'll be some downtime, which is never fun. And then you have this new cluster that you're working with, right? And so the things that you're going to have to mitigate with this solution is what do you do with those writes that occurred after you took the snapshot? So what some people would have done is they'd maybe write to a queue or Kinesis or something like that. And then once that new cluster is up, they'll sort of hydrate those writes. Not the best solution, but a solution. But there's a better solution, right? And this is what we're going to review right now. And so that solution here is zero downtime online resharding. So we just recently announced this, and we wanted to build this in a way that we knew our customers wanted, right? And we're going to talk about the difference that we've done and the enhancements that we've done with this operation. It's a little bit different than how open source does this as well. So let's kind of go back to that 3-shard scenario. Imagine you have 3 shards, and now all of a sudden you want to do 5. This is a very, very simple API. In fact, that's the CLI command for that API. What you do is you would pass the replication ID. That's like your cluster name. You would pass a parameter, which is apply immediately, basically if you want that operation start occurring. And then you would also pass the node count for the new shard, right? So in this case, 5. And this API is also true for scaling down. So if you wanted to scale down, the only additional value that you would pass is which nodes you want to get rid of. Now, everything after that is completely we're managing. We're doing for you, right? So what's happening here is there's zero disruption to your application. You're still using Redis just like you were using Redis. We're doing the resharding and doing a uniform slot distribution across these new shards. And slot by slot, we're migrating these shards in a very reliable and robust way, and you don't have to worry about this, right? And so one of the differences here that we did is with open source, there's a key by key migration. And we wanted to change that because when you do key by key, there's a possibility where your slot will be split across multiple shards. And that problem basically limits a few commands. For example, there's some Lua capabilities and multiple MGETs and things of that nature where you won't be able to use, right? So there's some limitations there. And then when a failure happens, it's harder to recover from that sort of scenario. So we decided to spend a little bit more time on this problem, and we changed that algorithm to do slot by slot. So we'll prevent the split slot scenario, and also we don't disrupt or change the behavior of your application. We're not limiting the commands that you need to run on this. Now the only con here is that there is a possible performance impact, but there is no downtime, right? So that's just one thing I'd like to call out. Now the same thing is true for scaling in, right? So you want to scale in, you have a cluster, and then all of a sudden you realize, you know what, I don't need all these additional shards. Our memory consumption is good enough, maybe it can support 3, just scale in. And how do you do that in an automated way, right? So now we're revisiting where CloudWatch sort of pairs nicely with ElastiCache. So let's say, for example, you had an alarm set on memory. And now that alarm went off, right? So your memory is high. What do? Right? So you can issue an SNS notification. That SNS notification, you're going to basically trigger a Lambda function, and that Lambda function is going to parse the notification, and then based on that alarm, it's going to do something. And in this case, we're going to add some shards. And you can automate this. So you can add the logic that makes sense to you to scale up and to scale down. Very similar to how auto-scaling groups would work for EC2. But in this case, you're sort of building that workflow using CloudWatch, SNS, and AWS Lambda. Now, the one thing I would advise if you're going to do this is to account for some of the time that it would take for the operation to complete. So you might want to be a little conservative with your metric associated to like memory or CPU or whatever you wanted to react to. And again, just like we talked about, as soon as you kick off that function, you're basically telling ElastiCache scale up, or scale out, rather, and then everything is back to normal, right? Now let's kind of look at this in another perspective. So imagine this is your application. Everything is healthy. And if you're a business owner, something good just happened. Now you have more customers. More customers are hitting your site, and they want to buy products. If you're an infrastructure or a developer, something bad just happened, right? Now you have heavy pressure, heavy load to your database, your application. So what you would do, again, just like what we talked about, you'd trigger an alarm, you'd scale up your EC2 instances, and very similarly, you can certainly have a conservative alarm to scale up your cluster. The added benefit here is that you're still sort of protecting your backend database. You're consuming that pressure in that cache layer, and you're leaving your backend sort of in the same state that it needs to be, which is really cost effective. Because scaling your database is costly, or can be costly with licenses and things of that nature. And then the other thing is that when you do something like this, your cache can support much greater operations per second. And again, the latency is much faster than a backend database. So this is ideal. So let's take a second here to take a look at Amazon ElastiCache security. We'll sort of review the basics and sort of build up from that point. So, kind of starting from a clear canvas here, imagine you have a VPC, three AZs that you're working from. The first thing that you'll do with Amazon ElastiCache is you'll define a cache subnet group. And this is basically a collection of private subnets that you would place your cluster in that really spans the AZs that you want to host your cluster in. The second thing that you're going to do is you're going to define a security group, which is very similar to a firewall that's going to have the port and also the protocol and then the IP or the security group that's going to have access to your cluster. And then you're going to place you're going to create that replication group, or create your cluster, and you're going to place it in there, right? So you're going to use that security group and a cache subnet group as part of that replication group creation. Now, if you were to take a snapshot and you wanted there to be some encryption at rest, we have that feature. That's a relatively new feature. So your snapshots will be encrypted. And then if you wanted application access, you'll build your application. There'll obviously be security groups that are sort of protecting your application. And then you'll enable traffic from your application security groups to your ElastiCache security group, right? And at that point, now you have access to your ElastiCache cluster. So this is a very secure environment. The only way you can have access to your ElastiCache cluster is if you enable access. Now, what if you wanted to have encryption between your application and your cluster? So encryption in transit. So this is also relatively new. So we just recently announced encryption in transit with Redis 3.2.6. And we also added Redis auth. For some folks who want to use that token-based authentication against the cluster using their applications, you also have that capability as well. So to sort of recap here, encryption is new, and this is both in transit at rest. There's nothing that you need to worry about with respect to keys and issuance and renewal of those keys. We're taking care of all that for you. And then it's from a HIPAA standpoint, if that's something that you care about, it's included in the AWS BAA. So it's a HIPAA eligible. Now we'll review some common usage patterns with ElastiCache. So this first slide is just really a kind of a slide to show different types of organizations that use ElastiCache. And really it covers all sorts of verticals. And as I mentioned earlier today, all sorts of workloads. And those workloads really span from caching to, sentiment analysis, and streaming data, some various things. And usually what happens is an organization will start with caching. Maybe they'll do like database caching. And then they'll move to maybe object caching. Maybe they'll go into API caching. They'll cache the responses for API requests. Maybe they'll start caching Elasticsearch responses. And then they'll kind of grow into other use cases. And then we'll start seeing additional things. We also see some organizations use Redis as a standalone database. And this is certainly doable, especially if you can recreate that data. Because again, you can take snapshots. You also have HA that you can do. So a metadata store or something that you can create is certainly possible. Let's take a look at caching. So with caching, typically the way people think about this is you're placing a cache in front of a data store, right, or a database. And you're caching the results that you would typically get out of that database. But where it gets interesting is imagine you have correlated data or data that spans multiple databases. So we'll just make up an example here. Imagine you had a customer where maybe you're capturing clickstream data for your particular customer. Maybe it's in Dynamo. Maybe that specific customer, you have transactional data like orders, order history, things of that nature in your relational database. And maybe you also have product metadata in your S3 object store. And what you want to do is, in addition to caching that backend data, you want to create like a cache hub. Right? You want to create a central location that really is capturing the activity of that user. You can easily do this. And some people do this with Redis. And what this does is it simplifies your data access. It puts everything in one spot for you. That aggregation is very natural with respect to how you might want to use this for analytics or various use cases for your application. And the one thing that you'll need to do is obviously make sure that you can trigger and keep that cache fresh. So whether it's through AWS Lambda or some other process that you might define, whenever you're updating that backend data store, just keep that cache as fresh as possible, just so that aggregated view is as accurate as possible. Furthermore, with caching, we also see organizations, taking caching, they're essentially caching everything, right? Including other NoSQL databases. And to some, this is sort of like, they think about this at first like an ANSI pattern. They're like, well, why am I caching in a Mongo database or Cassandra database? Well, you're doing it for the same reasons. You want to lower the latency, the data retrieval speed. You want to increase the data retrieval speed from your backend data store. And you may also want to lower your cost because, again, what Redis allows you to do is support incredibly high request rates at a low cost because you're not paying for that throughput or those requests to ElastiCache Redis. And there's various techniques that you can do to cache data, whether you want to serialize the objects that you get out of those backend databases, or whether you want to convert them into a hash map or something that makes sense for your applications. There's a variety of different things that you might want to do. It all really depends on what you want to, how your application wants to use that data. Another interesting pattern that we see a lot of organizations do, because Redis is very fast and very rich with respect to data structures, and there's a lot of aggregate data structures like the hash map, the set, sorted set, linked lists. What they might want to do is, as they're capturing fast-moving data, say maybe we'll go back to sentiment analysis. They're capturing tweets or things that are coming in very fast. Maybe they're using Kinesis streams for this. What they want to do is they want to interpret, they want to kind of dive into that data, and they want to enrich it, and they want to see if maybe that user did something previously on the system. So they'll peel off records from that stream, and then they'll take maybe the user ID or something that they can correlate to the cache, and then they'll query the cache, and they'll see, all right, do I have activity for this user? If I do, let's go ahead and summarize this information. Or maybe the data decorated. Maybe we'll enrich this data. And then after they create this aggregate view, they'll store this information in a cleansed stream. And then that cleansed stream now has a richer information, processed information, that they might have some other, process, maybe additional analytics that they might do, or might hydrate another backend database for that. Other things that you can do, we talked about PubSub. You might want to, if you saw something interesting maybe in that stream, you might want to publish that information to subscribers, and those subscribers are doing something with that data. Maybe you have a dashboard or something else. You can certainly build that with Redis. And as we're sort of talking about fast data, fast-moving data, Kinesis streams, this sort of big data architectures is becoming more and more popular with Redis. And what we're seeing people do is they, as they're processing information, they still want to have that data, in their big data lake. But what they also might want to do is they might want to augment that data platform that they're building and create this fast data layer, right? And this fast data layer is going to be for maybe, that transient information, the active data, and something that they can really pound on for a low cost. Because again, there's no added cost for that throughput and the requests. So they might use a variety of different engines or products to process the information, whether it's Kafka, Apache Storm, or Spark. And then they'll use a connector to basically drop that data into to ElastiCache Redis. And then once it's there in those data stores, they'll use a variety of different tools. It all depends on that workflow, and then they'll analyze that data both in the fast data store. Maybe they're also using, obviously, their big data lake for historical, maybe aggregations and things of that nature. IoT, we're seeing a lot of usage with Redis with IoT. This really depends on the use case, but what a lot of times happens is an organization, they might be building something and they don't know exactly at first, what type of data they want to store, for historical reasons, or they want to capture all the sort of sensor informations in the beginning and sort of kind of tailor it down to what they really need. And they're thinking about this, and they want to build a solution in the most cost-effective way that does not hinder performance. So what they'll do is they'll capture sensor information. They may use the AWS IoT service for this, which makes it incredibly easy. And then once it's in the AWS IoT service, they'll trigger a rule from the rules engine that might have a Lambda function. And then that Lambda function will essentially write data to Redis, right? And if this is time series data, this is very easy to do because you can capture the data and use a sorted set. And in the score, which allows you to sort the data based on that score, you can use a timestamp for that. And as you're writing the data to that sorted set, you can also have the properties of that sensor in a hash map. And wrap all that into a transaction would make a lot of sense. And if you also wanted that data for historical reasons, you wanted that raw data, also write that to S3 via Kinesis streams. So that would be an approach that we see some customers leveraging with ElastiCache Redis. Geospatial capability with Redis really was a game changer. So we talked to a lot of organizations who build mobile applications, whether it's a ride-sharing organization, whether it's an organization that has a recommendation engine, maybe a restaurant engine or something of that nature. And what they'll do is, maybe you're walking, they'll take the user's information, that longitude, latitude data, they'll pass it up, maybe through API gateway, they'll hit a Lambda function, query Redis with that geo information, and then recommend points of interest. This is incredibly easy to do with Redis. And again, Redis is very, very fast. So this enriches that user experience because your recommendations are happening at incredibly fast performance. And the only thing that you would need to do here is just define a workflow that's constantly keeping those points of interest fresh into Redis, if it's not your primary database here. So in this case, we're using DynamoDB as a primary database. We're using DynamoDB streams. Every time we write, maybe it's a restaurant into DynamoDB, that information will go through DynamoDB streams, be triggered off of a Lambda function, which will write that data into Redis. So in this case, Redis is really complementing DynamoDB. Ad tech is another use case that we see a lot with organizations using Redis. So kind of just to review the workflow here. So what you have is you have ad publishers who are essentially, placing ad slots for bids, right? And so they send this information, whether it's clickstream information, user information with a particular, ad location into this ad network. And then you have bidders who are essentially saying, well, do I want to bid on that and place my advertisement in that slot? And that logic that's involved there needs to happen incredibly fast, right? That entire workflow needs to happen in less than 40 milliseconds. So the most critical part here is when the bidder receives the information about the ad, they want to execute whatever logic that they have incredibly fast. So they need a really fast database. But what would be better is if the database provided capabilities to do really quick operations. So, Redis has various things with sets where you could do intersection, join, unions, things of that nature with a variety of other data structures. So they'll take advantage of some of those capabilities, do very, very quick, operations with Redis, and then go ahead and bid or not bid in this use case. Chat applications, we see a lot of this, especially with gaming companies. So if you're a gamer, maybe you're playing a game, and you see maybe chat happening in a campaign, a lot of communication happening within a group of players. That communication may be powered by Redis. Other times I've spoken with customers who, you'll be on a website and then a chat application will just pop up. That application is powered by Redis using PubSub capabilities. And then leaderboards. This is like a go-to solution with gamers because what you can do with a leaderboard, and kind of going back to the sorted set, is this gives you very, very easy ways to rank information and then retrieve information in various different different amounts of users. So for example, I can say, give me all the users with a specific rank, or give me the reverse rank of the first top users, things of that nature, natural operations that would happen in a ranking engine, which is a leaderboard, right? So you have that capability with Redis. Rate limiting. So we have organizations who, within their API calls, maybe they're building a solution where they want certain organizations to purchase maybe different packages of how many times you can call a specific API, right? So this is sort of bundled in different packages, maybe a silver, gold, platinum type of deal. And then what they'll do is in their in their API that the end user will consume, they'll make a call out to Redis, which is really, there's a variety of different ways you can implement this, but essentially you're using counters, whether you're decrementing or incrementing a counter, and then just making sure that that customer didn't hit that limit. And if they did, you're just throttling it. And again, they use Redis here for speed, and they also use Redis here because you don't pay for all those requests. So it makes a lot of sense to do something like that. All right, so let's spend some time here and talk about best practices. So the first one that we're going to view is sizing, cluster sizing. When you're building a cluster, there's a few things that you want to to really consider. The first one is storage, right? So this is sort of the default one. You'll want to take a look at how much data you actually need. And then you want to add 25% data. This is a data that you want to reserve for Redis, for those background operations that we talked about. And by default, we'll reserve that for you. And then the next thing that you want to do, and this is really optional, is you may want to add a little buffer for some growth, right? So that would be a healthy way to size your cluster. Now, the second thing you want to do is you want to make sure, and you want to review this with the developers if you're in the operations, or if you're a developer, you want to review this as well. You want to make sure that proper usage of TTLs is being done. And the best way to do this is really understand the frequency of change of the underlying data. So review how frequently that data changes, and make sure that whatever TTLs are being placed on that data reflects what the underlying change does. We talked about scale up and out using CloudWatch. So you may have a bunch of different alarms that are going to be set to proactively react to your cluster. And if you wanted to size for memory, you're going to select an R-based instance. R4s are great. They're memory optimized. But in addition to memory, they support incredibly high networking starting at an R4 large, for example, has 10 gigabits of network performance. So it's sort of network and memory optimized. The second thing you want to do is think about performance. So once you got sort of the storage out the way, you want to consider what type of operations are happening and have a game plan in terms of what you're going to do when one of those thresholds is met. So the first thing, kind of obvious, if you're spiking on read IOPS and you need more read IOPS, you're going to add more replicas. If you need more write IOPS, that means you need more shards. You need more primaries that you can write to. If you need more network I/O, if you're somehow you're being scaled on on network, you'll just pick a network-based instance. In general, if you're loading data, use pipelining as much as you can for bulk reads, bulk writes. And then consider the big O time complexity associated to the operations. And this one is sort of a bigger topic, but the point with this one is really understand, what is that operation, what kind of impact does that operation have on that data structure? How many members does that data structure have? And then what you can do to sort of reduce that speed or the worst case scenario associated with that operation. And then finally, the thing that you might want to do is think about, the different cluster isolations associated to your cluster. And what I mean by this is, when you create a cluster, there's a variety of different parameters that you can define. One of them is like an eviction policy. And what you might select for a caching cluster may be very different than what you might select for a metadata store. And so what you might want to do is have caching workloads in a particular cluster and maybe a different cluster for your queues, maybe another cluster for something else, your metadata store. So sort of group by purpose. And then the more granular you get here, the cost is going to go up. So you need to figure out what makes sense for your organization. The other thing that you'll always want to do is once you sort of have an idea of what makes sense from a sizing perspective, you'll want to test this. It's very easy to test this, and what I actually do is in my CloudFormation templates, I also build out an instance that has the Redis client built into it. So it's very easy for me to test the performance before I hand it over to somebody or before I start using it in a POC or a demo. So this is another way to sort of kind of stamp that you have a good idea that this is going to perform the way you want. Now, when you, we talked a little bit about eviction policies, and we'll just kind of talk a little bit further about this. When you create that cluster, if you're doing it for, for your developers, you'll really want to evaluate what this cluster is being used for. And how this data is being used more specifically, right? So the different eviction policies that exist, they're everything from an all keys LRU, which really takes any key, least recently used key across your entire key space. If you have, for example, a volatile LRU, you're basically going to evict a key that has that has an expiration set, right? So a TTL set. And the difference between the two is big, right? Because what if you have data that does not have TTLs, and then you also have data that has TTLs, but the data that doesn't have TTLs, you never want to evict because it's metadata, right? So this would be a reason why you might use one versus the other. And then so this is the kind of logic that you might have, and then the same thing is true here for the TTL, volatile TTL, and so on and so forth. From a CloudWatch perspective, you'll always want to look at CPU utilization. Make sure that you're sort of monitoring how much processing is happening on your cluster. If you feel that you need more CPU support, you might need more shards. From a swap usage, you want to see that low, if not 0, especially if memory is high. You never really want to be in swap in an in-memory system. From cache misses to hits, you always want to have more cache hits than misses, right? So you might want to target like a 90 and up ratio. That would be healthy. And so if you had all the things that we talked about, which was storage, performance, all those sort of things built out, but your developers aren't using the cluster effectively, it's kind of pointless, right? So you always want to sort of look at the cache hit to miss ratio. Evictions, you never want to see evictions. Even though we just kind of talked about which one you would select, really an eviction is happening when you're overloading the cluster, right? So the cluster is at least being nice to you and saying, before I get rid of a key, tell me what algorithm you want me to evict, and that's where you select those max memory policies. But ideally, you don't ever want to hit that scenario unless you have a specific use case, like you're using a Russian doll caching, or you define it as an LRU cache or something of that nature. From a connection standpoint, you always want to see this as stable. You always want to validate that your developers are using connection pooling, just like they would use with a database. And as we mentioned earlier, set alarms wherever you can. Keep in mind, from a client's perspective, a connection perspective, you can have up to 65,000 per node, whether it's a primary or a replica. There's parameters here where you can kill idle connections, whether you use a timeout or TCP keep alive. So you want to take a look at that and figure out what value makes sense for your organization. I mentioned here for reserved memory, we by default will reserve 25% of reserved memory. So that would be a recommendation there. And then setting the max memory policy, as we mentioned earlier. Now let's kind of take a quick look here at caching tips. So the first tip, as we mentioned earlier, understand the frequency of change of the underlying data. And what I always do is I always try to be a conservative with this, right? So the first question you want to ask yourself is, what's the impact if you provide stale data to the end user? And if the impact is high, then be conservative. If there's very little impact, then use your best judgment here and work with your your database administrators and your business owners to understand what value makes sense to place. As we mentioned, set the appropriate TTLs that match that frequency. Choose the proper eviction policies that align to the requirements. Isolate for purpose, which we discussed. Maintain the cache freshness through write-throughs. So there's two main patterns when you're dealing with a cache. So in this case, this is a kind of a cache aside. Redis is sort of on the side of your architecture, and what your application is doing is you're either lazy loading, you're checking your cache for a value. If it's not there, you're querying your backend database. You're grabbing the value from your backend database and you're hydrating your cache with it, with a TTL. So that way, the next request that comes in, the data is there. The other approach is proactive. This is where whatever process you have that's updating your backend database, you're also writing that data to the cache. Maybe you're applying a conservative TTL. So, if that data is not needed, that's okay. It's going to expire. But if it's needed, the request comes in, then you increase the likelihood that it's going to be there. And you're maintaining a better user experience because that data is always being found consistently in the cache. And so you're using both lazy loading and that write-through pattern with your cache. We talked about how to size your cluster, so you always want to do that. These are tenets to have a successful cluster. Monitor the hit and miss ratio. Use the failover API. I highly, highly recommend this. So we expose an API here that allows you to kill primaries. So do this. Make sure the applications are built in a way that can withstand failures. And the way you do that is by testing the failover API. And that's all we have today. So thank you guys for your time. I hope you learned something new with ElastiCache. Thank you.